So the final topic of this course is the study of modulations. And modulation is basically how you can add information to a carrier signal. The carrier signal is always a sinusoidal wave, shown here as a voltage, which varies as a function of time. It's an amplitude A times cosine of omega t plus phi. And so one can modulate any part of this. One can modulate the amplitude, one can modulate the frequency, and one can modulate the phase. Here we're first going to talk about amplitude modulation. And so the amplitude itself becomes a function of time. And we want to change the amplitude about some fixed value A0, not about 0. And M is therefore going to be our modulation index. And so we're going to say the amplitude as a function of time is that center modulation times 1 plus a cosine of frequency times a modulation index. And we want to make sure that M is in the range minus 1 to 1 so that A of t itself never goes below 0. And here I've illustrated with one fixed modulation frequency, but that could be more. So if we plug this modulation signal into A here, we can see what comes out. So here I've plugged it in. Here I've expanded out the thing there, and then we multiply this out. We get A0 times the carrier frequency. That's just the one part here. And then the modulation amplitude times this product of the two cosines. Now you can expand the product of two cosines as using the sum of angles and the difference of angles formula to get this. So a cosine, you take the sum of angles, which is cosine, cosine minus sine, sine, and the difference, which is cosine, cosine plus sine, sines. When you have both of them, the sine parts cancel, and you just get these two, and you get the half from each of these. And so when we plug in this varying amplitude, what we get out is a fixed frequency and then a sum of frequencies and a difference of frequencies in addition. And they're one on either side of the carrier frequency, a little higher and a little lower. So if we look at that, take a Fourier transform of that, or look in the frequency domain, what we see is that we have the carrier frequency in the center, that's this term, and then two sideband frequencies that are higher and lower by the modulating frequency. So now when you have a real modulation frequency, say you're trying to send the human voice over a much higher frequency carrier, what you get is not a single delta function on the side, but a band on either side, which will be identical, the two an upper sideband and a lower sideband that contain all the frequencies that are in your modulated signal. So just for reference, KSL radio in Salt Lake City, the carrier wave has a frequency of 1160 kilohertz, and so omega c for that is 2 pi times 1160 kilohertz. The width of the band that's allowed in AM radio is 10 kilohertz. So, so all the frequencies between here and here cover about 10 kilohertz. Now, since we're trying to broadcast radio with these things usually, and those radio transmissions take power, you don't actually want to transmit the carrier wave, and so one can filter it out. And so in that case you get what's called a double sideband suppressed carrier spectrum. And in fact you can filter even more and just give one side, so a single sideband spectrum. This is what's actually broadcast. In this case one would have to add the carrier back in at the receiver in order to deconstruct, to demodulate the signal. So I haven't told you how to modulate or demodulate yet. Turns out demodulation's much simpler, and in fact all you need is a peak detector. So here I have the standard peak detector, which we've seen before. When this voltage is greater than that voltage, a current can flow, and the capacitor gets charged up to match the highest part of this current. If this drops below this, nothing happens, but the charge slowly leaks across the resistor. And if you set RC to be 1 over RC to be less than the carrier frequency, but much greater than the modulated frequencies, then this will follow the modulated frequencies exactly. So you can imagine, here's my carrier frequency, the amplitude's going down, and the output of the peak detector, you see, basically follows the amplitude of this sine wave, which is decreasing. We have this decreasing signal. And this signal then you put through a capacitor and send to your speaker, basically.